the lecture for Chapter 20, Nuclear Chemistry. We are going to cover sections 1 through 3 and section 6 in Chapter 20, so this is your reading assignment. Let's focus on each section. Section 20.1 deals with nuclear structure and stability. Let's talk about the nucleus. We mentioned this earlier, but we're going to go into a little more detail about the nucleus and nuclides. What are nuclides? Well, first of all, let's talk about the notation that we're going to use. It looks very similar to isotope notation, where we have the mass number on top, we have the element symbol, and then over here we have the atomic number. Remember that the atomic number tells us the number of protons, whereas the mass number is the combined sum of the number of protons plus the number of neutrons. And therefore we can find the number of neutrons if we have the mass number and the atomic number. Remember, the mass number is the largest of the two and is written on the top, and then the atomic number is the smallest and is written on the bottom. To find the number of neutrons, you just take the difference between these two numbers, and it tells you what the number of neutrons is. This is going to be the notation that we're going to use for this chapter. So review it from chapter 2 so that you are able to identify the mass number, atomic number, and how to find protons, neutrons, and electrons. Although we're not going to deal with electrons much here. So let's talk about the structure of the nucleus. In this chapter, the protons and neutrons are going to be talked of in the general term of nucleons, okay, because we're talking about the nucleus. This is a nuclide, which is a stable or unstable isotope, so it's an isotope, but we talk about isotopes in terms of nuclides in this chapter. So it's just a term that we use, but it just means an isotope of a particular element, a nuclide. But the protons and neutrons, we're going to call them nucleons with a collective term. So the term nucleon refers to both protons and neutrons. And it refers to particles that make up the nucleus, obviously nucleons. They are held together in a very, very small space. Look at this. Approximately 10 to the minus 15th meter. That is a very, very small distance. And they are held together by the force that we call the strong nuclear force. This force, it is only evident in very, very small distances, like 10 to the minus 15th meter. Once we go beyond this distance and we start moving further on, the strong nuclear force drops sharply with distance. Therefore, it becomes kind of null and void when you go to farther distances. So it only operates over very, very short distances. What happens when you increase the distance between, so you go beyond 10 to the minus 15th meter, then electrostatic repulsions take over. So we look at the stability of the nucleus as balance between the strong nuclear force and electrostatic repulsions. If you think about the fact that what is the nucleus made of? Well, it's made of neutrons, we've said in the red here, and the protons in the blue. Well, think back about when we talked about the charges on these. We said neutrons do not have any charge, but protons are positively charged. And even though you have electrons that are circling in very ordered electron levels around the nucleus. The protons are in close proximity to each other. Look at these, they're touching over here. How do these protons stay this close to each other when we know that they're positively charged? Well, that is because even protons and neutrons, and you don't necessarily need to remember this, but even these particles, subatomic particles, are made of even smaller particles, positive and negative particles, that orbit them, kind of like the electrons are orbiting the nucleus. And those particles can attract each other because there's positive and negative particles, and they can attract each other. Now, when they're but that attraction between them is only, which is exemplified in the strong nuclear force, it's only evident when they're very, very close to each other. When they're far apart, then the repulsion takes over. So there's a balance between the strong nuclear force, which tends to hold these nucleons, these particles, together, and the electrostatic repulsion that comes from two positively charged particles being in the vicinity of each other. So if we talk about these two protons, for example, they're very, very close. So they're in this 10 to the minus 15th meter range. And at the beginning, when we have small nuclei, the protons are kind of close to each other, and they have enough neutrons around them to shield each other from that electrostatic repulsion. Now, as we add protons and neutrons to the nucleus, so that as the nucleus becomes larger and larger, this proton over here, for example, is close to this one, but it's not so close to this proton over here, which means that these two are going to repel each other versus these two who are going to interact through the strong nuclear force. And therefore, as the nucleus gets larger, the electrostatic repulsion between the protons starts to become more evident and compete against the strong nuclear force, making the nucleus less stable. And there comes a point where the nucleus gets so large that it is not stable anymore. In fact, for Z numbers, for atomic numbers over 83, meaning over 83 protons, none of those nuclei are stable. And that is because the protons now are so far apart from each other that they're not in this distance anymore, within this distance and the strong nuclear force, even though it binds some together, but the electrostatic repulsion between the protons is large enough to overcome the attraction from the strong nuclear force, and the nucleus falls apart. And it does so through radioactive decay. But just remember that the strong nuclear force is a very, very extremely strong force, but it only operates in very short distances. Once you go beyond those distances, the electrostatic repulsion between the protons is going to take over. Let's talk about the nuclear binding energy. This is the energy associated with the formation of a nucleus. So if I were to form, for example, this is a helium nucleus, which we know has 2 protons and 2 neutrons. If I were to form this, if I were to calculate the mass of the helium nucleus, by just adding 2 protons, multiplying each, so 2 times 1.0073 atomic units, which is the mass of a proton, so 1.0073 units times 2, because I have 2 protons, plus 2 times 1.0087 units, which is the mass of a neutron. And I could even add the mass of an electron, but it's so small. Anyway, if I add those up, I would get 4.032 units. Now, through experimentation, we can find the mass of one particular nucleus of helium, and its mass is actually 4.0015 units. There's a discrepancy between these two numbers, the ones that we just calculate and the one that we measure, and that is true for every nucleus in the periodic table. This is called a mass defect, and the mass defect is associated with a nuclear binding energy. There is sort of a loss in a little bit of a loss in mass when these particles come together and form the nucleus as when they are apart. And this translates to the nuclear binding energy, the energy that it takes or is released to actually form the nucleus. When the nucleus forms, it releases some energy because it's more stable in this form than these particles are in their free state. So in their free state, these particles have a little more energy than they do when they are together in the nucleus. And we can calculate that energy, the nuclear binding energy, via the Einstein equation of energy. So from the general relativity theory, we know that energy is equal to the mass times c squared, and we can calculate the nuclear binding energy for each nucleus in the periodic table. That relates to the formation, so this mass defect, we can convert it via this equation to energy and calculate the nuclear binding energy. This is the energy then that it's related to or is released once that nucleus is formed. It is also the energy that is required to break the nucleus apart. We have to provide that energy if we want to break the nucleus apart. Even though these are very, very small numbers in mass, it translates into a very large energy. That's why atoms, if we look at them, most atoms are pretty stable. That's because it takes a lot of energy to break them apart, to break the nucleus apart. We harness this energy when we have chain reactions or cascade reactions in nuclear reactors. This is what we're actually harnessing, is the nuclear binding energy, as those nuclei are being transformed from one to the other. As they decay, they release a lot of energy. So just remember that the nuclear binding energy is the energy associated with the formation of the nucleus, and it is quite a large compared to the energy of a chemical bond, for example, that we had been talking in previous chapters. This is very, very large compared to the chemical bonds that are being formed and broken all the time. We don't see nuclei being formed and broken all the time, other than the very, very large, heavy elements. This is not true for smaller elements, and that's because the nuclear binding energy is so large. If we were to plot the number of neutrons versus the number of protons for all the elements, we would find that there is this little blue line here. These are the most stable elements. Okay, this straight line represents a 1-to-1 ratio between the number of neutrons in a nucleus and the number of protons. And for smaller elements, till about 20 or a little low, we see that there's a good correlation between. It's a 1-to-1 ratio between the number of neutrons in their nuclei and the number of protons. However, if we get to larger elements, we see a deviation from this line, 1-to-1. ratio, we actually see it curve upward towards the number of neutrons. So there's a larger number of neutrons for these elements up here than it is than the number of protons. What happens is as we start adding protons to a nucleus to make it larger, heavier elements, we start to see that you need a larger number of neutrons to shield those protons and minimize the electrostatic repulsion between the protons. So neutrons act kind of as a shield between the protons that are far apart from each other to minimize the electrostatic repulsions and allow the strong nuclear force to glue those protons together, the nucleus together. And we need a larger number of neutrons as we increase the number of protons in a nucleus. And therefore, this curve starts to get closer to the number of neutrons. It curves upward. It's a steeper curve, which means that the number of neutrons is larger than the number of protons. Remember that the blue curve is the stable, these are the stable nuclei. Those that are non-radioactive, they do not transform into other nuclei. The most stable nuclei just like to be in the form they are. They do not convert into a different nucleus through radioactivity. This is because it takes energy, obviously. And so they're the most stable form. What is in the green over here are isotopes that do not fall into the stable category. And these are radioactive isotopes. And we're going to talk about each part of this green area, and we're going to talk about how these isotopes decay through radioactive decay. We're going to talk about the different types of decay, but just right now, just know that the blue line is the stable line and is called the band of stability, or the sea of stability. But the blue line is where the stable isotopes are located. In the green area is all of the isotopes that are not stable. And those isotopes are going to decay in such a way as to get closer to this blue line. So if they're over here, they're going to try to decay with a mode of decay that brings them closer towards this particular line here. Now, it may not get them directly on the line, but it would get them closer, so it would get them closer to stability. And I just mentioned that. Isotopes then will change the nuclear structure through radioactive decay. And there are 3 different forms of radioactive decay that we're going to talk about. The heavy isotopes, you can see these are isotopes with number of protons larger than 83 or so, meaning they have 83 protons in their nucleus. These up here. You can see there's no more stable isotopes for Z over 83. All of those isotopes, so elements over 83, number 83 in the periodic table, are unstable. They're all unstable because the nuclei get so large that we said earlier that the electrostatic repulsion is now, that's competing with the strong nuclear force, is now so large that it overcomes the strong nuclear force that binds the nucleus together, and therefore the nucleus falls apart. So anything larger than 83 or so, they're all unstable. They will all decay. And the most dominant form of decay is alpha particle emission, because they can reduce their Z number, the number of protons, very quickly with alpha emission to get back to this line. So we have those on top of this curve, so in the green area above this curve, will typically decay by beta emission to try to get closer to the curve. And then what is below this blue line here, if isotopes fall below this line, they're going to decay mostly through positron emission to get back to this particular blue line. We're going to talk about each of these in turn, and we're going to figure out how we can tell the mode of decay of a particular isotope if it falls in any of these green areas. We're going to talk about those, but right now just know that there's different emissions that are associated with these particular unstable isotopes, and they decay in such a form as they need to get to this particular band of stability, this particular line here, which are the stable isotopes. Well, through experiment, we have figured out that certain nuclei are more stable than others. We talked about how we can find the binding energy, and we can calculate the binding energy per nucleon, proton/neutron. So we can figure out the binding energy and then divide it by the total number of nucleon per nucleus and find the binding energy per nucleon. And if we plot that binding energy per nucleon versus the mass number, remember not atomic number but the mass number, which is the total number of protons and neutrons, we find this particular curve. And as you see that those elements that have the highest binding energy per nucleon versus the mass number, those elements are the most stable. And everything else is decaying to try to get to that number. If we have small or light nuclei, typically they fuse together to form larger nuclei because they're trying to get to these, what we call the magic numbers, the iron group of isotopes, which are the most stable. They're at the top of this curve. So lighter elements will fuse together in a process called fusion, which combines nuclei together to form larger nuclei. That's the process of fusion. Fuse together, right? To form larger elements because they're closer to this particular magic number here, the iron group of isotopes. And then heavier nuclei that are heavier than that, typically undergo fission or split. They split into smaller nuclei because they're trying to get closer to this area here, which is the most stable. The iron group of isotopes are the most stable, and therefore larger nuclei will try to undergo fission, so break apart to get to this particular area. We have also noted that nuclei that have even numbers of protons and neutrons, or one or both, are more stable than others, other isotopes. These are called magic numbers, and here they are. These are the magic numbers. So 2, 8, 20, 28, 50, 82, 126. You don't have to remember these necessarily, but these are numbers that are called magic numbers. So if the nucleus contains these numbers of protons or neutrons or both, then they are more stable. And these work just like the electrons for an electronic shell. We talked about the electronic shells and how they are filled, and once they are filled, they reach the electronic configuration of the noble gases, and so every element is trying to get to that configuration. Well, this is also true about the nucleus. They have those levels that are filled with even smaller particles, and the nuclear shells, if you will, instead of electronic shells. And these are the magic numbers that fill those shells. And therefore, those that have these are the most stable. You don't necessarily need to remember these numbers, but just be aware that there are these numbers that correspond to filled shells for the nucleus as well, and they're called magic numbers because they tell us that those nuclei that have these, they're the most stable. This is once again related to the nuclear binding energy per nucleon, and we just talked about that. So this is these elements are the most stable because they have even numbers of protons or neutrons or both, and they have large binding energy per nucleon. Okay, we're going to stop here for part 1 and then pick up on how to write and how to figure out how to balance nuclear reactions in the next section.